Hello, everybody. My name is Kevin Hoy. I'm a recent graduate from The Ohio State University, and today I'm going to be talking to you about the work I've been doing with Drs. Anil Pradhan and Sultana Nahar on Phosphorus 2 biosignature line ratios in exoplanetary and nebular environments. First, I want to go over why we chose Phosphorus 2 in particular. A huge reason is that it could be a missing link to finding life. It's a huge key element in DNA. As you can see in the picture on the right, you have phosphates connecting all the nucleotides together, which is necessary for building the long sequences necessary for the complex life we see here on Earth. And so what we can do is we can look for it in extrasolar planet star environments, just so we know if it is available for life to form. It's not technically a biosignature. If we find phosphorus, we can't just say, oh, we've probably found life. But we can't say if we don't find phosphorus, then it's pretty likely that we also won't find life in that system. And that was part of the big hubbub a few years ago. Phosphine was discovered on Venus, and so people were excited we might have found this big key ingredient that might mean something for the possibility of life on Venus. And it was also discovered in Cassiopeia A. It's been theorized that phosphorus is largely created in supernova explosions. So when we take an observation of a supernova, and if we find it, that's really exciting because it means we know where it comes from and we can start making some assumptions about how much of it we expect there to be. We chose phosphorus 2 in particular due to its low ionization state, which means that you don't need absurd temperatures to have an abundant amount of it in, say, the ionized upper atmospheres of exoplanets. And then there are also several key lines. Some of the biggest ones are at 25, 39, and 70 microns. Some of these are visible through the Earth's atmosphere, so we can detect them on the ground. Then there are also some key lines that are within the JWST range, so we can search for phosphorus using our big new fancy telescope. So how do I personally work to aid in the search for phosphorus? Well, what I work with are emission spectra, and specifically I'm working with a collisional-radiative-recombination model, which means our two means of populating excited states are electron impact excitation and electron ion recombination, and then we're only considering spontaneous emission down from those excited states. So now I'm going to go into detail about the specific parameters we use to model the physics we care about for our model. First, we have spontaneous emission. These rates are given by Einstein A coefficients, which describe the rate we expect to see transition from a given upper state to a given lower state without considering any kind of cascades in between, which will be important for another process. To get these, we use the code superstructure, which is a really awesome atomic code that produces a lot of information like wave functions, energy values, the A values we care about, and a lot more. This code uses a Breit-Pauli approximation, which means it does consider relativistic effect. It doesn't consider all of them, but it considers the most important ones. So that improves the accuracy of the code quite a bit. For electron impact excitation, we use another awesome set of codes called the R-Matrix codes, which also can produce tons of different atomic data. For us, we use them for collision strengths and the level-specific recombination rates I'll talk about in a little bit. For the collision strengths, they're all well and good for physics, but for our purposes, we need them to be a little bit different. So we process them into what are called effective collision strengths, which I'll go into more detail on in a little bit. For electron ion recombination, we're using the unified method of Nahar and Pradhan. These level-specific recombination rates are calculated using those R-matrix codes I mentioned, and many of them are publicly available on Dr. Nahar's online NORAD database. Then for recombination, we also need cascade coefficients, which, as I mentioned earlier, A values only consider direct transition from one state to another. But for recombination, we want to understand how an electron recombining into some excited state might decay into also populating some of the lower states beneath it. And for that, we want to consider every single avenue you have to get from that upper state to that lower state, including any combination of levels in between. I mentioned that when we're modeling electron impact excitation, and we first calculate what are called collision strengths and then process them into effective collision strengths. So I'll spend a little bit of time describing what I mean and why we do that. So these collision strengths, these describe the probability that an incident electron of a given energy will interact with an ion to produce a given excited state. And so you can see we have two sets here. On the left, we have some literature values from TIL 2004, and on the right, we have a big part of this work was that Dr. Svananahar has recalculated these collision strengths, including many more energy levels within the ion. So we believe these new values on the right to be much more accurate. As you can see, there's fairly substantial difference between the two. So the issue with working with collision strengths is that they care about electron energy, and they're highly resonant. They have very strong resonant structures. So, as much as we would like to, we can't know the energy of any given electron out in space. And it's very important that we know more or less exactly how much energy that has, because a very minor change in energy has a very strong change in collision strength, as you can see here. So it makes them very difficult to work with when we're modeling real plasmas out in space. So instead of working with collision strengths directly, we process them into what are called effective collision strengths. To do that, we may not be able to know the exact energy of any given electron out in space, but we do know that as a whole, they'll very closely follow a Maxwell-Boltzmann distribution according to the temperature of the plasma. So what we can do is average over the collision strengths with the Maxwell distribution function, and that will produce the effective collision strength. Whereas before, collision strength detailed the probability that an excitation occur as a function of electron energy. Now these effective collision strengths give the rate at which we expect to see those for a given temperature within the plasma. So as you can see here, we compare our results to those from the literature values TIL 2004. You can see some fairly substantial differences between the two. So what do we do with all of this data? Well, we feed it into the code that I've been working with called Spectra. The code was written about 30 years ago in Fortran, and what I've done is I've taken the original code and translated it into C++, while also including this new recombination function, which hugely improves the accuracy of the model. Along the way in the translation, I've sped up the runtime a little bit. I've added some new functionality that makes it easier to use, and that's something we'll continue to be doing in the future. So what you see here are some of the results of our work. We're comparing three lines here. The red line is there are the line ratios calculated using the collision strengths calculated for this work, including recombination. The black lines is using those collision strengths without recombination, and the blue line is calculated using the effective collision strengths from TIL 2004, also without recombination. And as you can see, our results in both cases differ from those used calculating using TIL's values. And incorporating recombination also has a major effect. So this tells us is that the new code we're producing, modeling more physics, is much more accurate. And so these new lines we also expect to be much more accurate to what we would see out in the universe. And here are more results from our work. These are line ratios that are specifically within the range of JWST spectrometers. And what we're comparing here are the different temperatures. So you can see along the x-axis is the density. And here are more results from our work. Here we've specifically selected ratios containing only transitions that are within the range of JWST spectrometers, and now we're also plotting for temperature. So you can see along the x-axis the line ratio depends on electron density, and now in the different colors you'll see how it reacts to temperature. So what's next? Well, I'm going to continue improving and adding functionality to Spectra. This will not only make it a more useful code that's able to do more things, but I'll also be working to make it easier to use. We're also going to be combining results from my code with my colleague Michael Rothman's GN4XOP code, which is used to model absorption, to create a complete simulated exoplanet spectra, which includes both absorption and emission across multiple ions and molecules. Just to sum up what I've talked about today, we have combined spontaneous emission, electron impact excitation, electron ion recombination to produce a model for phosphorus 2 emission, as we could see in exoplanetary atmospheres and star formation regions, which could perhaps be a clue to finding new life in the universe. Thank you very much for attending my talk. If you have any questions, I'm happy to field them at hoy.104@osu.edu. Thank you very much for having me, and I hope you enjoy the rest of the conference.